Hi, welcome back. We're in lecture 22 and the topic is nonparametric statistics. In segment 2, we'll cover some examples of nonparametric procedures that correspond to some of the more popular parametric procedures that we covered earlier in the course. So I just picked two simple procedures to cover because, again, it would be too much to try and cover all of the procedures or all of the corresponding non-parametric procedures for everything that we did in this course. It would require a whole nother course on non-parametrics. So I'm just going to show you two, and two that correspond to the sort of the simplest and most popular tests that we covered in this course, which are just t-tests. So the paired samples t, or dependent t, and the independent t-test. So the corresponding non-parametric procedures for those are known as Wilcoxon's ranking method or Wilcoxon's signed rank test. It goes by a few different names. I prefer just Wilcoxon's ranking method because that's actually the title of his 1945 paper where he introduced this method. And then the Mann-Whitney U-test is the corresponding method for an independent t, which is really just a modification of Wilcoxon's procedure. So you'll see in the R output it actually refers to it as Wilcoxon's procedure, even though most people know it as the Mann-Whitney U test. So to do this one more time, we're going to go wine tasting. Last time, we'll bring back these wine ratings. So first, let's look at the Wilcoxon ranking method. And as I said, you can look up the paper from 1945 where Wilcoxon introduces this method. He actually introduces a method for both paired samples T and independent T, but then Mann and Whitney came along and modified the independent method. So in this method, this is for a paired sample T. This is a non-parametric approach. The null hypothesis says that the median difference between pairs is 0. And we're going to deal with the median because, again, we're doing a non-parametric procedure probably because we're dealing with data that are not normal. Maybe there's extreme scores in the distribution. Remember, when you have that kind of a distribution, the median is often a better measure of central tendency to be dealing with than the mean. So that's why that's the null hypothesis. And then the alternative, of course, is that the median difference between the pairs is not equal to 0. If we wanted to do a directional test, we could say greater than or less than 0, but let's make it non-directional or two-tailed and just say not equal to. The example I'm using here comes from the old example we used back earlier in the course on wine ratings. So remember we had wine experts rate wines, 2 wines from each country. So there was a red and a white from France, and the same wine expert rated both the red and the white. So we have the same wine experts giving 2 ratings here. So this is a paired, we could do this with a paired t-test. But if you remember, the white wine distributions, they weren't normally distributed. So we would be violating some of the assumptions, one of the main assumptions of a t-test. So let's do Wilcoxon's procedure instead. It looks pretty clear that the whites are preferred over the reds in the French example, but let's do Wilcoxon's procedure to make sure that's the case. So the way this works, and it's a little, sounds a little convoluted at first, but let me just walk you through an example, or 2 quick examples by hand, and I think it becomes rather intuitive. So remember, it's sometimes known as the signed rank test. So what that means is, I just listed out a few rankings here, and this is an example where the null hypothesis would be true. There's no difference in the medians. And the way this works is, you take the ratings, so here are the ratings for 4 experts on red and white, and arbitrarily pick one as the positive condition and arbitrarily pick the other as the negative condition. So here I decided if they rated a red higher, then I'm going to give it a negative sign. And if they rated the white higher, I'm going to give it a positive sign. So that's where this column comes from, the sign column. If red is greater than white, then I give it a -1. If white is greater than red, I give it a +1. Then what we do is we calculate the absolute value of the difference in the two ratings. So you can see I ordered them already. If they weren't ordered already, then the next step would be to order them according to size, and then rank them according to the absolute value of the difference between ratings. So I'm just going to rank them 1, 2, 3, 4. Then finally, the last step is to take the product of the sign and the rank. And that's why it's sometimes called Wilcoxon's signed rank test, because we take the product of the sign and the rank, and then we add those up. And in this case, they add to exactly 0. That's what you would expect under the null hypothesis. Because you can see there's one, this rater rated the red greater than the white, as did this rater, but the two in the middle did the opposite. So there's no effect here. The reds were liked just as much as the whites overall across this little example. Of course, that's not what it looks like in our example, right? It looked like, according to the graph, if we go back a slide, it looks like the whites were preferred over the reds. So let's just set up a tiny little data set with just 4 raters that looks more like that. Here, you see that the whites are all greater than the reds, so my sign for each is going to be positive. I could rank them according to the absolute value of the difference. Then there's the ranks, 1, 2, 3, 4. And then finally, in this last column, I take the product of the sign and the rank, and then take the sum of those. And now the sum is 10, versus before it was 0. 10 is the highest possible rank sum of ranks we could get in this example. So that would obviously indicate a significant difference between these two conditions. That's exactly how this procedure works. We could just do it with all of our ratings, but remember we had 100 wine raters, so I'm not going to do it all by hand. I just plugged it into R. So here's what the output looks like. We'll do this in the next lab. There's a function called the wilcox.test. That's the name of the function. I put in my variable names, the French red, the French white. I had to say paired equals true because these came from the same wine raters. And this V is the value of the sum of the product of sign times rank. Remember, we took each sign times the rank, got the product, summed them. That gave us this value V, which in this case is 189.5. It's really high because there is a strong preference for the whites, right? And that gives a very low p-value. Now it's important to note that p-value isn't based on a sampling distribution or anything like that. It's based on what's the probability of this outcome happening relative to all other possible outcomes, which we can obtain just from the rank value. So notice there's no degrees of freedom because there's no family of distributions to choose from. We just calculate a p-value directly. It's a direct probability calculation. That's how non-parametrics work. So this is clearly a significant difference even in this non-parametric procedure. So now let's look at the independent case. So that was for paired samples or dependent. In the independent case, the procedure is called Mann-Whitney's U-test. And it's based on a paper by Mann and Whitney in 1947. Again, they just adopted Wilcoxon's procedure. Wilcoxon actually developed the procedure for both paired and independent, but Mann-Whitney improved upon it, so now it's known as the Mann-Whitney U-test. And the key to this test is you just arrange all your observations, regardless of group, into a single ranked series. And keep in mind that the sum of all the ranks is going to be equal to the total number of observations times the total number of observations plus 1 divided by 2. So again, that's why I'm doing this on a small scale rather than the whole wine rating example. So for example, if we just had 4 raters like I just showed you in the paired samples case, then it's 4 times 5 divided by 2 equals 10. 10 is the highest possible sum we could get. And that's what we got in the second example I gave you. We just had the ranks were 1, 2, 3, and 4. Sum 1, 2, 3, and 4, you get 10. That's the highest possible sum we could get. The Mann-Whitney U, the value is the sum of the ranks from the highest possible sum you can get, this value, minus the sum of ranks from one group. So if it's sort of like split half and half, so some of them are at the top and some are at the bottom, then we're going to get a U value that's about half of the highest possible sum. So again, let's illustrate that really simple with just 4 raters. Here's an example where the null hypothesis would be true. I just put this first and last rater in group A, and if I sum their ranks, I would get a sum of 5, and the same for group B. Right? If I sum their ranks, I would get 5. The total of all sums is 10, so in either case it would be 10 minus 5. My Mann-Whitney U value would be 5, or half of the total possible sum. That's exactly what we would expect if the null hypothesis were true. In this example, it's completely different. So in group A, they had lower ratings than in group B. So now the sum of the ranks in group B is 7. If I took the difference between the highest sum possible, 10, and 7, I get 3. That's the lowest U value I could get in this tiny little example. Again, I don't want to do that. I want to just plug it into R. So to do a non-parametric example for an independent groups example for our wine ratings, again, I wanted to take the white wines because those were not normally distributed. And we're just going to compare Australia to France. Again, it looks like there's not much of a difference, but let's plug it into R and see what we get. Here's the output. Notice that R does not call it a Mann-Whitney U test. They're pretty good about their history and statistics. So they just call it a Wilcoxon test. You put in your 2 values, and here you have to say paired equals false because this is an independent, the equivalent of an independent t-test. We get not a U value, they give it W instead for Wilcoxon. But look at the p-value, it's 0.39. Not significant, not even close to being significant, because there was very little difference between those 2 groups. Okay? So to wrap up this segment, there are lots of non-parametric procedures available to you. There are non-parametric procedures available for all the procedures that we covered in this course. Here in this lecture, I just illustrated 2 of them. So 2 of the simple and popular tests that we covered are paired samples T and independent T. Those are parametric tests. Here in this segment, we just illustrated the analogous non-parametric procedures, which are known as Wilcoxon's ranking method and the Mann-Whitney U test. And those are the non-parametric procedures that you can use if you violate assumptions and you can't overcome those violations of assumptions, then do the non-parametric procedures outlined here.